Hello, so after having understood BGT based current mirror, let us have a look at MOSFET based current mirror. So on your screen, I have two MOSFETs and both are of the type NMOS. It is called M1 and this MOSFET I am naming it as M2. Now look at the arrangement. I have a voltage source V plus that I am connecting right here because the net names V plus are same. So there is a physical connection between the two nets. So I have this positive voltage supply here, and then through the resistor, I am making a current flow through the circuit, which is called as I reference. It is also called as I in. So whether I call it I reference or I in. Now this input current has a value that can be your specification. For example, if I am asked to design a current mirror for a reference current I reference is equal to 4 milliampere, then I will have to write the equation, a KVL in the input side of the circuit to design the value of a resistor, to select the value of a resistor that will make the 4 ampere milliampere 4 milliampere flow through the circuit. So now this I reference is coming right here, which is then split into two parts. One is called as ID, which is the drain current through the MOSFET M1, and then this current is going like this into the gate IG. Since we know that in MOSFET gate is insulated, the gate current is zero ideally. And then I see another arrangement where ID, where the drain terminal, this is the drain pin, this is the gate pin, and this is the source pin. So drain and gates are shorted together, making the voltage difference between gate and drain VDG equal to zero. This arrangement is also called as diode connected transistor. In the case of BJT, we have seen that, right? But in case of a MOSFET, we we connect the drain and gate together so that this MOSFET will operate always in the saturation or active mode. So now in a moment, I'm going to explain you what is saturation and the active mode. Before that, let us understand this circuit. So 4 ampere millicurrent is the required one. So this drain current I reference is equal to ID. Here we can write is equal to ID because your IG is 0. Now I said VDG is equal to 0 because drain and gates are shorted. So I can also write that VDS, which is the voltage difference between drain and source, is equal to VGS, which is the voltage difference between the B and G, the gate and the source. So that's it. So essentially, this reference current is producing a voltage drop VGS across the gate and the source terminal of this MOSFET. So let's say the MOSFET has VGS equal to 2 volt. I want VGS is equal to 2 volt. That is what I want to produce. So what I will write the equation that is the KVL, Kirchhoff's voltage law, V plus, which is this voltage source, minus I reference time R minus VDS and VGS are same, minus VGS is equal to 0. So for example, I will say this is my 5 volt, that is V plus is 5 volt, and the current is your 4 milliampere requirement. So I reference times R minus 2 equal to 0 right here, and then it will be 3 I reference times R, and therefore I reference is given and R would be equal to 3 divided by 4. And accordingly, you can say that uh, this will be the value, that is your 3 by 4 will be your value of the resistance that you need to choose. This is 4 milliampere. Okay, now I have chosen, let's say, 1 kilo of the resistor. Then what would be the current that will flow through the transistor? That can also be decided. So I will say uh, 5 minus 2, that is 3, equal to I reference into R, and I reference therefore will be 3 divided by 1 kilo ohm. Uh, right, R has been chosen to be 1 kilo ohm here. So I will have about 3 milliampere current flowing through the circuit. Okay, now this VGS is there, and and I would say how to choose VGS. I said VGS is 2 volt. So VGS can be chosen, let's say the threshold voltage of the MOSFET should be known. So VTH is the threshold voltage, which is the turn on voltage of the transistor. If it is like 1 volt, then I am choosing the VGS to be 2 volt, 1 volt greater than it. So VGS minus VTH is called as V overdrive. V overdrive. So V overdrive voltage is 2 minus 1 equal to 1 volt. So that's the overdrive voltage. Now this VGS voltage, which is ready here, becomes an input voltage for the MOSFET number 2, that is M2. So here is your gate terminal, here is your source terminal, and that's the VGS 2 of this MOSFET. And we make sure that M1 and M2 are identical in properties and in size, so that their length of the MOSFETs are same, width of the MOSFETs are same, and the threshold voltage are also same. If they are all same, then we would say that M1 is equal to M2. So you see now I have chosen this NMOS both transistor to be identical. With that, I would say that this drain pin and the gate pin of the MOSFET, they are also at the same potential, right? And therefore, the VDS here, VDG actually, VDG is also 0. So if that is the condition, so for both M1 and M2, your drain pins are at the same potential, source pins are at the ground, and the gate voltage is also same, then I would say I reference get copied into the drain current pin of the MOSFET number 2. Therefore, my I out will be written as, which is I out here, will be written as I reference. And I would say I out divided by I reference is equal to 1. This is how I can design MOSFET based current mirror. Now I said in the beginning that MOSFET M1 and M2 both need to be operated into the saturation or the active region. So what that means? That means here we have an IV characteristics of the MOSFET, where IDS is your drain to source current, VDS is your drain to source voltage. For each value of the VGS, you have the current flowing through the MOSFET like this. Let's say this is VGS1. So initially, for when you apply an electric field between the gate and the source, and between the drain and the source, then you have a current ID flows through the MOSFET. So initially your current rises linearly, but after you certain voltage, if you still increase the VDS more, then your channel is pinched off. So channel is pinched off means no more current can flow from drain to source of the MOSFET, and your drain's current is said to be saturated. There is a constant current that you flows. Then you apply, increase the VGS again, then you will have larger drain to current. But after some time, if you increase the VDS, then you have VGS2, for example. Again, the drain current is saturated. And this cycle continues for every value of VGS. That is how the MOSFET works. So now you will say this part, this side of the characteristics is called as linear mode of the MOSFET. It is also called as triode region of the MOSFET. And this part of the MOSFET is called as saturation region or active region. So current mirror works on the principle that M1 and M2 both are operated in a active or saturation modes where the current is still constant. Now, before I take you to the simulation part of it, where we will run two analysis. One is .op and one is .dc sweep, where .op will give you all the currents and voltages and will help us to understand whether the voltages at the drain are at the same potential, whether the VDG of both transistors are zero or not, and whether, most importantly, the currents I out is equal to I reference or not. If that is the case, then we will say we have designed the current mirror accurately. Otherwise, we need to tune in the parameters. But before I take you further, I would like to show you the principal operation of the MOSFET again. Here on the theory, we see that this is the circuit where I reference is being flown into the circuit by the means of resistor, which helps us to do that. An input side of the circuit, this one acts as current sink, because you are sinking the current I reference into the MOSFET. And then with the conditions we just analyzed, we would say this I reference gets copied into the output transistor now, which is M2. And then this output side of the circuit is called as current source. Now we would say that the voltage at the drain and the voltage at the source of the output side of the transistor is given by the voltage between drain and gate, which is this one, plus the voltage between gate and source. So VDS is equal to VDG plus VGS. When your current is flowing and the transistor is biased into saturation mode, there is a relationship between the current and the voltages. So ID is said to be the function of VGS, which is applied between gate and source, and also the voltage between drain and gate, voltage between drain and the gate. So the equation for the ID, which is the drain current, is 1 over 2 Kp W over L VGS minus VTH whole square in bracket 1 plus lambda into VDS. Further simplifying this gives us the final relation, which is 1 over 2 Kp. Kp is some fitting parameter. W is the width of the transistor. L is the length of the transistor. VGS is the voltage between gate and source. VTH is the threshold voltage of the transistor, and the difference between is called as overdrive voltage, what we just saw. Then in bracket, lambda is called as channel length modulation. Channel length modulation is a concept where with the increase of the voltage difference between drain and source, your current slightly increases. We can say that LENGTH, channel length modulation. So we can show that by means of the curve. We just analyzed and said that IDS and the VDS current is constant all the time. However, in practical situation, your current is increasing slightly with increase in the VDS. And therefore, for this green curve, your output resistance is infinity, and for the red curve output resistance is not infinity. So here lambda is equal to 0, here lambda is not equal to 0. And This is how an output resistance is basically the resistance between drain and the source pin of the MOSFET. Now, the expression for the output resistance RO is given as 1 over ID in bracket 1 by lambda into R plus VDS, which can be simplified to 1 by ID. VE is the fitting parameter, L is the channel length, plus VDS. So you see that output resistance with increases with increase in the VDS and you for a given value of ID. There is one more concept of uh, so before that, I would say to keep the output resistance high, this resistance should be as high as possible. Your drain to gate voltage should be greater than or equal to 0. So here is your drain, here is your gate. And when you copy this current into the output part, I out is equal to I reference. We are seeing your difference between drain and the gate. This is VDG should be greater than equal to 0 volt. That means the lowest output voltage that results in the correct mirror behavior, which is called as compliance voltage, is the compliance voltage is should be equal to VGS for the output transistor to keep the output current level with VDG equal to 0. Let's come back to our circuit now, and we are all set with the basic understanding to simulate it further and know the operating point. So I have chosen the 1K value of the resistor. With this, I would see how much current can flow into the MOSFET. So what I have done, I have just taken the MOSFETs from the component library. I have taken this component and MOS4. So it is an N-channel MOSFET transistor with explicit substrate connection used for monolithic MOSFET. So here is the fourth pin, which is called as substrate or body. I will tie it to the source, which is, you can see, I have tied the source terminal to the body of the each of the transistor. Now I have taken 5 volt here. I have resistor equal to 1K. Before that, I would like to show you the operating point analysis, right? So we will do one thing. We will click run and we will see what are the voltages and the currents into the circuit. So here V plus, which is the voltage here, is 5 volt. Then voltage at net 001, which is possibly this net, is 4.77 volt. Then voltage at I out, this net is 5 volt, which I have explicitly set to keep that minimum voltage across the output transistor so that it remains in a active mode. Then voltage at the net 003. Now, what is that net? We need to understand, which is 0.1581. And then voltage at the net 002 is also the 0.152. So how about we just name that net and then we simulate it again. So let us do that. This net is I out, and this net maybe I would call it, let's say, VDG. That is the voltage between drain and this one. So why not just name it? So I have named it like here, and this is the same net. And these are the ground nets that is right here. Let us simulate again and see these things. So okay, so is basically V of VNOO2 and VNOON, they are these nets that is between body and the source, and they are at the same voltage 0.15 volt. Now most important parameter, the current through the transistors, which is ID of M2. This is the output transistor and output current, which is 0.2 milliampere right here, and the ID of M1 ID of M1 is also 0.2 milliampere. Look, this has a minus sign here and this has a plus sign. It means we have a gain of -1. So the current magnitudes are same between input and output current, but output current is in the opposite direction to the input current. Okay, now the currents are same, that is what we want, and this circuit acts as a current mirror. Now if you want to analyze the gate current, IG of M2 is 0 here. Similarly, IG of M1 is 0. So as expected, we say that the gate is insulated, the current through the gate terminals will be 0. Similarly, the source current then of MOSFET 2 and the source current of MOSFET 1, which will be equal to the drain currents of the respective transistors, since the gate current is 0, right? Unlike BJT, where you have a value of base currents that gets multiplied by the beta of the transistor to get you the collector current, okay? And the current through the transistor, through the resistor that you are letting flow is 2 milliampere. So what is the VGS now? So VGS we can calculate. So at this node, you have like 4.77 with respect to 0. So 4.77 minus 5 minus 4.77 is like 0.3 volts. So 300 millivolt is what you drop across the resistor. So that is how you can see that. Now you have got this current mirror. What we'll do, we'll see the compliance voltage, that is the required minimum voltage to keep the output transistor M2 in the active mode so that your circuit works as a current mirror. So for that, we will run the DC sweep analysis. I will enable this analysis by removing this sign, click OK, and I see now I have DC voltage source that I'm sweeping from 0 to 5 volt at the step of 0.1 volt. So I will click OK. I have got this curve, and on the schematic, you see if I take the cursor here, there is a black probe which is prompting me to left click my mouse to plot the current through M2, which is my drain current. I will click OK, and here you go. And here you see that I have this current and it is almost in the linear mode or in the triode mode until I have a 5 volt, 4.5 volt, and after that it's saturating. So how about I need to increase the voltage? I would sweep this DC voltage source from D0 to, let's say, 10 volt, and at a step of 0.1 volt. We'll see how it gives. Much better. Here I have, after running the second analysis, up to 5 volt I have to keep across the transistor M2. Okay, so that up to this level or just below the 5 volt, I need that much voltage across transistor M2 to keep it in the active mode, which is this region. Okay, otherwise below 5 volt I'm operating the transistor in the triad mode where current is not constant, but here is the constant current. How about plotting the current of the transistor M1, which is, look, the blue line, which is constant to your 240 230 microampere, which is 0.23 milliampere, which is what we did and we saw through the operating point analysis. So this is how you can simulate your current and voltage characteristics. Let me plot, add plot pane, and here I'm going to plot the VGS of the transistor or the drain voltages of the transistor. So let me plot this node. This is VDG, which is also VGS of my transistor M1. And if I plot this voltage, uh, okay, this is actually simulating this because I'm sweeping this voltage. So VI of out is nothing but this DC voltage source that I am sweeping linearly. So you actually can see my VTG is about 5 volt constant, not 5 volt. is 4 point, let me 4.7 volt, what we saw in the DC point operating point analysis. So that is the VGS I have to keep. So maybe I need to increase the supply voltage so that there will be a maximum drop, more drop across R1, and the VGS can be reduced to this one. So I leave it to you for further analysis. So hope you understand how to design the MOSFET current mirror and how to analyze various voltages and the currents, and accordingly you can try to play with the circuits. Till then, wish you happy learning.